All right, so when in polar form, we talked about this kind of at the beginning before I had to get into grading. But if I'm looking for the modulus or the argument, you just have to look at it and you know your answer. So what is the modulus? Yeah, well, I'll spell it out. I was just going to do R, but just so you know. And then what is the argument? If you just said R, I'm good with that. And if you just said theta, I'm also good with that as well. So if you want to shorthand it, but that was the first part of this process. Is that easy to write with? I like it. It's nice. Okay, so you got the modulus and your argument, easy to identify, and then it says turn it into rectangular form. So the first thing you want to do is turn these trigonometric functions using the unit circle to figure out what the rectangular coordinate plane is. So at cosine pi fourths, what is that? Square root 2 over 2. Did we do this yesterday? No. I think it was my 6th period. Was it this period we did? We did the first one. Okay, so it's like, man, I'm like, we'll do it for the video. After this point, what do I do next? Something. What's the thingy? What's that thingy called? Multiply straight across, or what's the other word? Distributing. Very good. So I'm going to distribute. So I get 2 square roots of 2 over 2. So again, you put this over 1, multiply straight across, numerator to numerator, denominator to denominator. Hopefully at this point, we're getting a little bit better with multiplying fractions. After this point, what do I see about the 2's? Very good. So I get the square root of 2 plus the square root of 2i. If you put the I in the front of the square root, like some scholars, I'm totally good with that. It just, to me, i's always goes at the very end. But I can also see how this can be confusing if your square root goes a little bit further than normal. Questions on this part? We all get this right? All right, this was on your test, so if that's one of the questions that you struggled with, make sure it stays in your pocket. Thank you. Make sure you know it now. Again, you should be able to log in through Clever, go to Great Minds, and see your test now. So you can start kind of reviewing the things that you got right versus the things that you got wrong. So when you do come to tutorials, we can kind of focus on the things you didn't know. Unless you just happen to guess it right, then we need to go over that as well. But you know those things. Just to give you an idea with that hour tutorials that we have to maximize the time. All right, same process here. What is my modulus? 5. What is my argument? Two pi over 3. Okay. Gotcha. Okay. And again, you just pull it straight from that. So now I'm going to work it out. At cosine 2 pi thirds, what do I got? Very good. And what is sine 2 pi over 3? Perfect. And then now what do I do? Distribute. So again, you can put that over 1, multiply straight across. So you get what? Perfect. Can I cancel anything or simplify anything? No, so I leave it like that. Do not turn these things into decimals. Leave them as that. That is the correct formatting. Then we keep on going. What's the modulus for 3 here? 3 square roots of 2. Very good. The whole part would be part of the modulus. And what is the argument? Very good. Working it through. Cosine at 7 pi fourths is? Perfect. Again, you can put this over 1, distribute by multiplying straight across, numerator to numerator, denominator to denominator. And when I do that, what do I get? Very good. So when you are multiplying this, multiply your outside numbers. There's technically not, there's like an imaginary 1 there. So 3 times 1 would just be 3. So 3 just sits there. Then multiply the inside of your radical. So square root of 2 times square root of 2 gives me square root of 4. If you know that it's going to simplify down to 2, I'm totally good with skipping these steps. I just want you to see the entire process so you understand how we got 6 when we get to that point. And then here, this is like a minus times a 3, which gives us a negative 3 look. Square root of 2 times square root of 2, again, gives you that square root of 4, and the 2 on the bottom, and then our I. Now, square root of 4, we now know is what? 2. So again, I want to write this out again as 3 times 2 over 2 minus 3 times 2 over 2i. You can do this in 2 ways. One, you can go ahead and tell me what is 3 times 2? 6, and then divide it by 2, which gives you 3. Or what do you notice about the 2's? They can cancel just like you saw on number 1. I think that's a little bit easier to do, but I'm good either way. So I'm going to cancel out these 2's. And regardless of which direction you went, you should have gotten 3 minus 3i. Everyone good? All right, let's continue on. Number 4. What is the modulus on 4? 3. What is the argument on 4? Do we all know how to read Roman numerals? And I represents 1, V represents 5, X represents 10. If a smaller letter comes before a bigger value, you subtract. If it goes after, then you add. So an I represents 1, a V represents 5, and since 5 is larger than 1, then we know we need to subtract. So that's how they get 4. Just an FYI. I think this is actually a teak in 3rd grade or 2nd grade, or at least it was when I was in school. It's when I remember it the most. No? I'm almost positive it's an SAT question, at least one. And it's like, what does this Roman numeral represent? And it has like the X, which is 10, M, which is millennium, which is 1,000, C for century, which is 100. That's how we get century and millennium. I think, I don't know the symbol for score, but score is 20. You get that from Abraham Lincoln. 4 scores, and yeah, so that's 80 years ago. Most of our math come from them. All right. Yeah. So if you want to go back, you know who to blame. All right. So cosine 7 pi over 6 would be? Yep. Again, what do I need to do? So when I do that, again, this becomes a 3 times a negative. So it should be represented as negative 3 square root of 3. I did not multiply an outside number with an inside number, so I just kind of wrote them all out. Over 2, I don't remember if it was this class. I think it was actually next class. If there is a negative involved, you must put the negative first. You cannot write this as 3 negative square root of 3 because it's going to look like a minus sign, right? So make sure the negative always goes first. And then minus 3 over 2 because that's what 3 times 1 is. Can I cancel or reduce anything? No, so I leave it as is. We still good with this? So another one, make sure we fully got it. What is my R? 1. Now, they were nice by writing it out, but what if there was nothing here? What would it be? Still be 1. Very good. All right. What is my theta or my argument? Just pi. Very good. So I'm actually not going to write the 1, or do I need to write it? I need to see it with the 1. It will be, right? So if I was to write the 1, maybe I didn't notice it. Cosine of pi is -1. And then what's sine of pi? 0i. What's going to happen to that 0i? Just disappears. So my final answer is what? -1. This is the answer that you would see if you wrote it out as -1 plus 0i. You're not wrong, but this is your cleaner number. Okay. Questions on how to pull information from polar form or how to go from polar to rectangular? All righty. On part B, you were asked the same questions. What was the argument and modulus of each complex number? You don't really have to explain it to me. As long as you know how to do it, then you're pretty good. How do I calculate the modulus first? Which in this case would be 2 squared plus -2 squared. Now, let's say I'm doing my test. If I forget this negative, is that a big deal? No, it's not, because a square of a positive and a square of a negative is still what? Still going to be positive. So if you're getting negative results because you're kind of maybe a little calculator dependent and you use the negative, that's fine. Just make sure you use parentheses in the calculator so that you do get that positive version. But also just note that it's supposed to be positive. So if you're getting a square root of a negative number, pump your brakes a little bit and go, there's something wrong here. Also, if you get the square root of 0, that should only happen when? What? Not when there's a 0. Well, I know, but like what coordinate would give you a distance of 0 from the origin? 0, 0. If you're given the coordinate 0, 0 to start, obviously that's the only one that would get 0. So if I was plugging this in the calculator and I got 0 as an answer, I say again, pump my brakes and go, I think I did something wrong because I shouldn't be getting 0. I should get something other than that. All right. So just some things to kind of keep an eye on. So 2 squared is? Negative 2 squared is? 4 plus 4 is? 8. Again, on the test, I did allow this. I went back, I think it allowed it on some, and then, yeah. But if you had to reduce this on the SAT test, do remember that this would be 2 to the 4th, 2 times 4, and then that's 2 times 2. Takes 2 of the same numbers to come out, and then I have a leftover of 2. I do recommend that you practice this technique because this is what they'll do on the SAT and ACT. This will not be an option. It's just the computer program accepted it, and I wasn't going to argue it. All right. Questions on how to simplify a square root, because I know that's a big struggle. All right. So again, that's the modulus. How do I find the argument? It is very good. So that's going to be tan inverse of what? B over A. So in this case, it's going to be negative 2 divided by 2. When you are doing the argument, the sign actually does matter. So make sure you don't forget the sign. But what is tan inverse of negative 2 divided by 2? Is it 45? Okay. A lot of y'all missed half a point on one of the questions because you did not remember where the quadrant is. I think on one of them, if you would have typed it in the calculator, you would have got like 16 point something or something like that. But you had to pay attention to what quadrant you're in, because I think on that one, it were in quadrant 4 or something like that, and it was actually a negative, and some of y'all just made it a positive all of a sudden. You had to add 360 to it. So I think the answer should have been like 337 or 347 or something like that. But yeah, I forgot that step. So in this case, what quadrant is 2, negative 2 in? 4. So what do I need to do with this 45 degrees? No, it's add, but are y'all sure y'all got 45 degrees? Okay, it should be negative 45 degrees, which is what you got on your test as well. And then you were supposed to add 360 to that. I can write a 6, which will then give me 315 degrees. Some of y'all got it wrong because y'all wrote the degree sign because it said degrees in the sentence. I went back and overrided that and gave you full credit because I thought that was dumb on taking that off. But yeah, questions on that if y'all made that mistake. All right, let's finish up 3B. So again, I'm looking for the modulus. That's going to be the square root of 3 square root of 3 squared plus 3 squared. When you have a coefficient outside of the square root and then a square root, you do need to apply the square to both of them as such. So 3 squared would be what? 9. And then the square root of 3 squared would be what? 3, because the square root and the square root cancel. So you end up with a 9 times 3 here. All right. Plus, what's 3 squared? 9. What's 9 times 3? 27 plus 9. Square root of 36. 6. I don't think it was on your test, but I think it was on one of y'all's homeworks or something like that. A lot of y'all would reduce it, but then you would keep the square root. If the square root is an even number, the square root goes away. So this is a solid 6, not a square root of 6. So do watch out for that as well, because I would hate for you to do all the work and get it wrong just because you put a square root back into it. Right? Your argument, again, is tan inverse of b divided by a. So this is going to be 3 square root, or 3 divided by 3 square roots of 3. A couple things too. Don't worry about reducing the inside fraction unless you really want to. I hate for you to have to come up with an error here and then end up with the wrong answer, even though your setup was right. Right? But regardless, what answer did you get in the calculator? 30 even. Okay. What quadrant is this in? Do I need to do anything? Nope. So there you go. Questions? I think the hardest part is this part right here that I saw a lot of y'all struggling with. Make sure y'all know how to square a number and with a coefficient and a radical. All right. All right, so again, I'm going to do the same work. Square root of -1 squared. Notice every time I do have a negative, I am applying parentheses around it, just so if I plug this into the calculator, I don't forget to apply it to the negative. And then it's always plus square root or negative square root of 3 squared. You can. You really can. Yes. Absolutely. -1 squared is 1. Very good. What is negative square root of 3 squared? Just 3, right? Because a negative and a negative is going to make a what? Positive. Again, that's how we always know we'll end up with a positive result. So if you're thinking the negative needs to stick around, it does not. What's 1 plus 3? Square root of 4. I like these nice clean numbers. Again, to find the argument, tan inverse of negative square root of 3 over -1 will give me 60 even. Okay. What quadrant am I in? I'm in the, which one? The third. So remember, the calculator will give you a range between 0 and 90 every single time. So if you're looking at that, you'll always kind of fall in either quadrant 1 or 4. That's talking about the graph of a tan inverse, but y'all don't know that yet. Y'all will get to that point eventually. But you got to pay attention to the coordinate. So the coordinate here is a negative comma a negative. So then I know I need to fall in quadrant 3. So in quadrant 3, what do I need to do? Plus 180, and that gives me 240. Any other questions like that? Caleb, too easy for you? No. Wait, what? Oh, that's what I'm saying. Too easy? Seems too easy. It's good stuff. All right, so here we go. I'm missing my A. So what it needs to go there? A 0. Do I have to put the 0 square to get the answer? No, you do not. You can keep it as just this. But again, make sure you're only applying the B, and I'm not bringing the I in this. If you try to bring the I in, then that's how you get that negative result, because I squared is -1. So just watch out for that as well. And I've only seen that mistake happen when it's just an imaginary number. Right. So anyways, -5 squared is 25, and the square root of 25 is 5. Very good. And then our argument, what? Okay, this right here would be -5 divided by 0. So this happens twice because you got undefined, correct? So you only get undefined 2 times. It either happens at 9 degrees and at 270 degrees. And I love Braden's outlook here. We realized that the imaginary number was negative. When the imaginary is negative, it's always going to fall at 270. And if the imaginary is positive, it's going to fall at 90 degrees. Okay, so you only get undefined twice, either here or here. Positive would be 90. Because if you have an A and not a B, you'll get 0, which either happens here or here. So then again, you can look at the real numbers, and if it's positive, then the answer of 0 will stick. But if it's negative, then the answer of 180 is what needs to be changed. So again, this would be 270 degrees. Questions? All righty. All right, last one, and then we'll kind of go over that one question. I think it was question 12 when it said z to the fourth. We're going to see a pattern here, so that problem will actually become a lot easier than what you had to do on the actual test. All right, but here is a real number 1. So again, I'm going to look for the modulus, which again would be 1 squared plus 0 squared. But what's 1 squared? And what is the square root of 1? 1 in itself. So still a 1 there. So also, if you notice, if you're just left with a real number, the distance will just be that real number in itself. Same concept with the imaginary. It's always going to be their absolute value if it's just by itself. So that modulus gave you a 5. If this would have been a negative 1, the answer would have been a positive 1. Absolute value just meaning distance from 0, or how y'all always remember it, it's always a positive result from absolute values. But if you don't remember that, you can always go through the process, just kind of showing you some tricks there. All right, tan inverse. This again gives you the 0 over 1, which if you plug that in the calculator, it gives you 0. All right, but that again happens twice, either at 0 or at 180. The issue is you need to know this coordinate here is 1, 0. Where's that going to fall? The right side or the left side? The right side, so the answer of 0 would stick. Okay. You could actually get away with this answer as well. Both of those would technically be correct. I will say this on an SAT question, pay attention to the interval when they give this question. If you see something like this, which one's my actual answer? This means that theta has to be between 0 and 360, but this says 0 less than theta, less than or equal to 360. So in this case, 360 would be the only answer. So when you're like, oh, this test has 2 answers, well, pay attention to what's given to you in the top. And it could have also done that in a reverse way. It could have said this right here. So now what's my answer? 0. So on the SAT question, when you get to something weird like this, and you have like 2 potential answers, go back to the information given and go, all right, where's it one in between? Sometimes you also see it between 0 and 2 pi with the less than or equal to. Oh, okay. All right. So any questions on any of this? Go ahead. Mm-hmm. All right. So this was an exploratory challenge. If you started it because you finished the opening exercise yesterday, let's see just how far you went. So this is basically trying to get you to understand that z to the 4th power on the test, which without actually having to do this part right here, which is what we were taught in the previous topics. And then you would have to distribute, and a whole bunch of times before you finally got an answer. In this challenge here, we're going to actually identify that there is actually a simpler way and a pattern that always works. All right, so first thing it wants us to do is just rewrite each one of these as a rectangular form. So we're going to go through the process of doing it the long way and then see if we can identify a pattern. Remember that 1 plus I squared is 1 plus I times 1 plus I. How would I work this out? Distribute. So I got 1 times 1, 1. 1 times I, just I times 1, I times I. Which does turn that into a negative 1. So when I work this out, what's going to happen to the 1s? You can turn into a 0. Very good. So they cancel each other out. And then I plus I would just give me 2I. Remember, when you are adding or combining like terms, you just add their coefficients. It only becomes a square when we multiply. Right? Any other questions there? All right, so that was a nice simple one. Now, when we look at 1 plus I cubed, this can kind of go back to when we discussed just regular I. Go ahead. Right, but we don't have to do it necessarily again since we've already done the work. That's what I was about to get to, is 1 plus I cubed is the same thing as 1 plus I squared times 1 plus I. Do you agree or disagree? Agree, right? Because this represents I have two of them. This represents I have one. So that would go back to a cube. Well, you already calculated what this is. It's 2I. So instead of pulling that out again, just go ahead and replace 1 plus I squared with that 2I to make your life a little bit easier. And then now how would I have to work this out? Distribute. So 2I times 1 would be, and then 2I times I would be 2I squared. And what's going to happen to that I squared? Negative, so that 2 will become a negative 2. Now write this in the correct order. Very good. Random thought when you asked that question in the middle of another thought. I took a class in college called paleobiology. Paleobiology. I'm a geology minor. So I took the course because I thought it'd be the study of fossils, like dinosaur bones. I was like, oh, I like Jurassic Park. That was a great series, right? Okay, that was one chapter out of like 18. Yeah, so that was a rough course. Anyways, this professor was about 97, I think. And she would get her scrolls out, and as she was teaching, she scrolls like rolls out, and it's like a brownish looking paper. Anyway, she was just start teaching from it because a lot of the fossils that there she was there for, so she knew exactly what they were before they became fossils. Totally kidding. She was just really old. Anyways, though, a kid, there's like 120 of us in an auditorium just writing down what she's saying, but this kid stops her and asks a question, and she goes, like, I think she just realized that there were people in the room with her, and then she goes, and then just kept on going, like completely ignored the kid's question. I was like, note to self, don't ask her questions. Anyways, that just made me think about that because I was about to say the same thing that you were about to ask, but I could see how a professor goes, if you would just let me kind of finish that. But sorry. No, you're good. You're good. I'm not mad. I was just, I don't know, my brain. All right. So 1 plus I to the fourth power. You can do this in a couple ways. You can break this down as like 1 plus I times 1 plus I cubed, or you can break this down into 1 plus I squared times 1 plus I squared. What happened? So you good? Oh, okay. So 1 plus I fourth. I find this to be easier to go 1 plus I squared times 1 plus I squared. Now the reason I went this direction rather than 1 plus I times 1 plus I cubed, because if I do 1 plus I times 1 plus I cubed, it'll be this times 1 plus I. So then I'll have to do a whole bunch of foiling, which is you'll get the same conclusion. But notice 1 plus I squared, what did I get as a result? 2I. So it's a lot easier just to go, if I split this up into square and square, I can just go 2I times 2I, which will give me what? 4I squared, which will give me what? -4, right? And we get a lot quicker of an answer versus doing 1 plus I times -2 plus 2I, but you'll get to the same conclusion. So if you didn't notice that, you'll work out regardless. Any questions on that? Yes. Yes, you can. All right, so now with all that done, let's fill out a chart and let's see in a chart form if you can identify any patterns. So I'm going to plug in the stuff that we know. 1 plus I squared, what do we end up getting? It's like -2 plus 2I or something. Okay, what's the square? Oh, just -2? Oh, just 2I. Okay, so 2I. What was I cubed? And then what was 1 plus I? Fourth? What was it? -4. Okay. So the other stuff we didn't talk about, but we can talk about real quickly. Anything to the 1 power is just going to be what? Itself. So I can just rewrite it as 1 plus I. 1 plus I 0. Anything to the 0 power is what? 0. So it's just going to, oh, sorry. Anything to the 0 power is what? 1. All right. Anything to the 0 power is 1. Have y'all seen the proof on that? Okay. Okay. The sky is purple too. Do y'all believe that? No. Why are you arguing now? I can prove that it's purple. But you don't. You're in the room right now. You should know this as well. You should know anything to the 0 power is 1, and you should know the proof behind it. But I'll save you some time. Okay. All right. All right. Do you see any patterns so far on what happened from one thing to the next, to the next, to the next? Look, kind of like what we saw when it was just an imaginary, right? We went from imaginary to a real to a imaginary to a real, kind of switch that direction. So I see that. Started with a real, went to a complex, went to an imaginary, went back to a complex, went to a real. So we wanted to finish that pattern, go to a very good. So there's somewhat of a pattern. Can you identify like maybe where those numbers came from? Like why we went 1, then 2, then 4? What do you think the next round would probably be? I like it. That's a potential thing. Maybe. That's what I would like to argue. Hmm? Yes, we're going to identify a pattern, which is going to identify a formula. Again, last class likes to say I like to gatekeep things, and I'm gatekeeping this right now, but we're going to figure it all out, and then you can identify any answer you want depending on whatever power you have. So we can do 1 to the 22nd power and get the answer in like 1 step. You'll see that here in a second. Well, before we get there, we have to do all the fun. So what is the modulus of 1? 1? Square root of 1, which is just 1. Whoever, yeah, sorry, that was one of y'all that said it, right? And we did this earlier in the opening exercise. How would I find the modulus of 1 plus I? Okay, so this is going to be the square root of 1 squared plus 1 squared. What's 1 squared? 1. And so what's 1 plus 1? 2. So I get the square root of 2. Do I need to show all of those steps, or do y'all see how this becomes this? All right, I don't have that much room in a box. All right, this one is going to be 2i. We just talked about this in the opening exercise. Without doing any math, what's the modulus going to be? Okay. Again, without doing math, you could just say it's 2. It's going to be the absolute value of whatever the real or imaginary term if you're just left with just 1. But again, if you would like to do the process, by all means, you get to the same conclusion. Next part is going to be the square root of -2 squared plus 2 squared. And we did this in the opening exercise. What did we get? Which is? Oh, gotcha. That's the answer. You got the square root of 8, which is 2 square roots of 2. And if you need to know how we did that, go back to the open exercise to see the breakdown. What would the answer be for -4 without doing work? Just 4, because it's going to be the absolute value of whatever that number is when it's just one single number. Any questions there? Okay. Do you see anything? See a pattern here? What do you see the pattern as? Not quite. Okay, that's a pattern. Okay. Every 2 steps, what's happening every step? Okay. By changing by I to re. No, they're all. Oh, those are none of those are complex. Remember, modulus is always a real answer, real number. Anyone see it? By what? It is dilating by something, huh? No. It's something, right? David said that every 2 it's multiplying by 2, which is true, but I want to know what's happening every step. Huh? Very good. If you notice, this is actually multiplying by itself by the square root of 2 every time. 1 times square root of 2 is square root of 2. Square root of 2 times square root of 2 is square root of 4, which is 2. Square root of 2 times 2 is just 2 square roots of 2. Then 2 square roots of 2 times square root of 2 would be 2 times square root of 4, which is just 2 times 2, which is 4. So that's a good pattern. Where does the square root of 2 come from? Okay, so you see we are multiplying by the square root of 2. But where does square root of 2 come from? Anyone know? Not tan? Not tan, no. You said, though, it's dilated, right? By a scale factor, and then we thought about it, and you said square root of 2. How do we find dilations? No. How do you find dilations? It's on your test. Huh? What about a unit vector? It's the distance formula. It's the modulus, right? What is the modulus of 1 plus I? Square root of 2. So even though this example is being multiplied by the square root of 2, you can figure out what your modulus is going to keep being multiplied depending on how many you have, because it's going to be multiplied by its modulus. So if I was to change this to a 3 plus 4i, and I was looking for 1 plus, or this to the fourth power, I could easily identify what its modulus would be by determining how many times I'd have to multiply it. So for instance, anything to the 0 would be 1. Square root of 2 to the 1 power would be what? Square root of 2. Square root of 2 to the second power would be what? 2. Square root of 2 to the third power would be square root of 2 times square root of 2 times square root of 2. One of them would turn into a 2, but then I would still have a 2 in a square root. And then to the fourth power would be 4, because it ends up being 2, 2, 2, 2, which is 16, which ends up being the square root of 16, which is 4. So you can see that no matter what it is, I can identify the modulus super easy now. All right, so that's cool. I can identify the modulus super easy. Does everyone see how that works? So this right here would basically calculate your modulus. We can write a formula, and we'll say r to the nth power, and I'll call this guy an n, to the degree. Right? So whatever degree you're raising it to, you're going to raise your modulus to it as well. So we just saw if I'm raising to the fourth power, I can take square root of 2 to the fourth power, and I would get 4. All right? So therefore, we just calculated an equation for modulus for anything with a degree. Okay, that's the first step. That's the first part. Second part, let's look at. Go ahead. Oh, to the fifth power. So you would have to do square root of 2 to the fifth power. So in my thinking, I would say, all right, square root of 2 to the fifth power is the same thing as the square root of 2 to the fourth power times square root of 2. Well, if I know that the square root to the fourth power is 4, there it is. What would be the next one? 8. What would be the next one? What would be the next one? 16. And then you can kind of see that continuation, right? All right. But that works out for all of them. So this is a guaranteed formula. Let's talk about argument, though, right? Because we can always identify our complex number if we can get it into polar form with a modulus and an argument. But let's see if we can easily identify an argument as well. What's the argument of 1? And how would I find it? How do I find arguments? B divided by A, right? Which is what we did in the opening exercise. So the argument for 1 would just be what? 0 or 360. We're going to start off with 0 degrees, though. All right. What is the modulus of 1 plus I? So again, this would be tan inverse of 1 over 1. What would that give me? 45 degrees. No, that's my degree symbol. Okay. So this is 45 degrees. And since I'm in quadrant 1, did I have to do anything? No. All right. What would then be the argument of tan inverse of 2 over 0? Right? That would give you undefined. But then the imaginary part is positive. My answer will instantly be 90 degrees. Okay. Okay. What is the tan inverse of 2 over negative 2? because you see the pattern already. All right. What would you get in the calculator? You would get negative 45. What quadrant would this be in? 2. And what do I have to do to that? Plus 180, which then gives me 135. I love that you already identified the pattern. What's the pattern going by? It's adding. Oh, my bad. I wasn't supposed to say that part. It's doing what with the 45? It's adding 45 degrees. All right. Okay. So that'd be tan inverse of just, what was that? 0 over negative 4, which again would give me tan inverse of 0 over negative 4 would give you what in the calculator? Zero over negative 4. It gives you 0, right? And that happens twice. Either happens here or it happens here. But this time the real number is a what? Negative. So it's going to be 180, which goes back to our original pattern. What's 135 plus 45? 180. Okay. So that all checks out. All right, so since you've determined that we are adding 45 degrees, where in the world did 45 degrees even come from? So if I'm adding 45 degrees, where did 45 degrees come from? That's actually how you determine tangent, but we're not there yet. How did 45 degrees get here? Huh? This is a true statement. It is half of 90. Will I always be adding 45 degrees? No. Just like here, I multiplied by square root of 2, but I won't always do that. I determined that that square root of 2 came from the what? The modulus. Where's the 45 degrees going to come from? Not the modulus. Huh? The argument of what? Of the z, the original z, right? So, and we can see that the original z calculated to what? 45. So if I want to know what I'm adding each time, I just need to calculate the argument of the original z. So let me do that as argument of whatever the original z is. Now, here I was multiplying, so I was able to do r to the nth power. But here I'm adding. So if I'm starting here at 45 degrees and I get to the square, I would do what to find its argument? So if at 1 degree it's 45 degrees, and at 2 degrees it is 90, how do I get from 45 to 90? Add 45. Okay, that's fine. If I'm at 45 degrees and I want to know what the third power is, what am I going to have to add? Well, from 45. Oh, yes. Yes. Okay, good. Sorry. So at the fourth power, what am I got to do? There you go. So if I want to know whatever the argument is, depending on the power, instead of raising it, I'm just going to multiply it by that n. So this is going to be n times whatever that argument is. So if I have a fourth degree, I would calculate my argument, in this case 45 degrees, multiply by 4, I instantly got 180. If I was doing to the 25th power, I don't have to do all this work. I can just go, all right, my argument is 45, multiply that by 25, and I get some argument. Please put that up, Ileana. Go ahead. That's it. Yeah. So the n, when I talk about n, I'm talking about whatever that power is. So whatever that power that you're given, find the argument, multiply it. Now you have the argument. Now, the cool thing about this, now that you're able to easily identify the modulus and easily identify the argument, we can plug that into polar form, work that down into a complex or a rectangular form in one easy step, rather than having to do this times this times this 4 times like you did on your test. So when you come take your retake, if you need to take a retake, you're more than welcome to use this pattern. All right, so let's kind of put all of this together. So what patterns do you notice each time you multiply by another factor? You can say that the modulus is going to be whatever the modulus is, raised to the nth power. The argument is going to be n times whatever the argument of that power is, or that complex number. Any questions there? I still got 2 minutes. Ain't it 40? Oh, it's 40, 41's the last class. All right, so that's a good stopping point. We'll continue this discussion tomorrow during Halloween and give you some time to practice.